Yeah, a very good morning to all of you. So today we'll be learning about the external inductance. Last class we saw about the internal inductance. So welcome you all. If you are new to the channel, please like, share, and subscribe our channel. So we'll start with the external inductance and the phenomena related to it. Last class we saw the internal inductance and we saw the formula for it was L internal. We calculated L internal and it was half in 10 power minus 7. We saw it was Henry per meter. Okay, so now about the external inductance. What is the external inductance and how to calculate the external inductance, and finally the total inductance of the transmission line. Now in order to calculate the external inductance, we have to assume a point like if this is my circle over here, so I'll redraw it properly. So if there's a circle over here, and what I want is that I want to calculate my external inductance. Suppose this is a circle, okay, and I have a point, 2 points I have. One point is here somewhere, this point at the outer periphery, okay, and I have one more point over here. So let this point be here, okay, and in between these points I have two more. I have two more points over here. So let these be okay. So I'll be using different colors so that we understand it in a much better way. So from point number one, this point, to the other point, I have a distance of around, this point is an internal point, so let this be point P1. I have a distance of D1 and an external point that you can see over here. Let this be another point like Y1, or and this would be another distance here would be D2. So in between these points, what I notice is that I have a radius over here. So my radius point is surrounding here, suppose. So this be point X here, and this is a small distance, small strip over here. This small strip over here represents dx. So what I am doing is I am considering an external point now. Until us we were considering, now the external point is the point between P1 and Y1. So consider an external, what, magnetic flux. Consider Hx and external to the conductor. Let's consider this external to the conductor. Okay, external to the conductor. It's external to the conductor at radius x, which is greater than r. See, earlier we saw that the radius was outside. Now this is x, which is greater than r. So in the previous slide, if you look back to my previous video lecture wherein I create for internal inductance, please revisit it so that you will be able to follow that. There I had this ix and I separately, but herein I am taking this ix is equivalent to I, because I am considering the radius not equal to r but it is equal to ix, and ix is greater than r. So what I am doing is ix is getting replaced by I, and the flux density at x becomes, so now the flux density which I arrived, flux density at x would become, at x becomes, so it will become equal to, now see, bx we saw from the previous, bx is nothing but mu naught hx, and mu naught is 4 pi into 10 power minus 7. So instead of mu naught hx, I can write in terms of I that we derived lastly, that is mu naught by 2 pi x. So this equation we have derived when we were calculating the internal flux. Now since the entire current I is linked by the flux outside the conductor, so the flux linkage that would be d phi x. So this flux linkage d phi x would be numerically equal to what? It would be equal to your flux, that differential flux. So here this differential flux, what we are seeing is, so So this differential flux, what you are seeing, d phi x for a small region of thickness, region of thickness dx dx, and let us suppose 1 meter length. Okay, so 1 meter length. So we are considering 1 meter length of the conductor. So now the numeric equation for this to calculate the other parameters, like, so d phi x is essentially here equal to d phi x, so which is nothing but your magnetic field intensity into the length, and the length is 1, so this is nothing but equal to mu naught I dx by 2 pi x. Nice. So now we are seeing, if we go back to our previous slide over there, which just now we saw, see here. So if we see, the distance over there was 2 pi x, but here if we have to integrate for external flux, so to into the region for integration would be between d1 and d2. So that region of integration to calculate the flux over here would be between these 2 points, that is your d1 point and d2 point. So here, if we have to calculate the total value of the external flux, so what we need to do is, the external flux linkage is between 2 points, okay, that is p1 and y1, and these 2 points are separated at distance of d1 and d2, and this would be found by integrating d phi x. So how it is found, the total flux? So d phi x we need to integrate, okay, and the region would be d1 to d2. So to find the total flux phi x, we need to integrate the region d1 to d2 d phi x. So that is nothing but, what we need is v naught I by 2 pi. We need to integrate between the region d1 and d2, which is 1 by x dx. So after we are integrating this system, so we arrive at an equation, that is your mu naught value, 4 pi in 10 power minus 7 into I. So this is for mu naught I am putting, this is my 2 pi, so 2 pi, this is 2 into 10 power minus 7, and 1 by x will become ln, okay, ln of x between d2 and d1. So once we are substituting this equation, so we will arrive at another equation, and the equation here would be, final equation what we get is 2 into 10 power minus 7 I, sorry, okay, this would be 2 into 10 power minus 7 I ln of d2 by d1 and Weber per meter. So this is the thing. So now we found out that our L external value is nothing but 2 into 10 power minus 7 I ln of d2 by d1, and our L internal value we saw that was equal to 1 half of into 10 power minus 7. So these are the two values which we found. Our L internal value we found was half in 10 power minus 7, okay, and our L external value we found that, okay. So this value will be, sorry, this is not Weber per meter, this is Henry per meter. Similarly, this is also Henry per meter, and this was also Henry per meter. So now unlike in order to calculate the inductance of a single phase line, okay, so what we need to encounter is that we have to calculate the inductance for a single phase line. So in order to calculate the inductance of a single phase line, what we do is, we take inductance of a single phase line and try to explain you how do we go about it. So let's go for the second part of it. So, and let's see the total inductance and how it goes. So this was about the internal inductance, and this was the external inductance. Now let's go into the understanding of the internal, okay, inductance of a single phase 2 wire line. So basically when we are understanding this inductance, so we know that we will be having two conductors. Okay, so one would be of radius r1, another would be of radius r2. Suppose one conductor is for the return circuit. Okay, one conductor is the return circuit for the other one. So first let's consider the flux linkage of the circuit caused by the conductor in conductor 1. So what will happen is that a flux will set up current in the conductor 1 at a distance equal to or greater than d plus r2 from the center of the conductor. Conductor 1 would not link with the circuit. So let's analyze how it is happening. So basically what happens is that let's analyze. We have two conductors. Okay, one conductor is here, another conductor is here. Okay, so let's analyze this. So this conductor is having a radius of r1 and another conductor is having a radius of r2. So they are separated by a distance of d. Let's suppose they are separated by distance of, here I wanted to write d, so somehow it became o. So let's consider 1 meter length of single phase line consisting of two solids. So I will write down, consider 1 meter, okay, length of single phase line consisting of two solid conductors, consisting of two solid conductors. So these are our two solid conductors. Okay, and these are and two solid conductors separated by a distance d, as you can see over here. These are two solid conductors which are being separated by a distance d over there. So the two conductors are separated. So what happens is that the conductor 1 carries current 1 referred into the board. So conductor 1 would be carrying a current referred into the board, and second conductor is carrying a current that is referred outside the board. So that means the current I1 would be equal to minus of I2. So current 1 is the current entering and current 2 is the current leaving. So the most important factor over here is that we are interested to calculate the total inductance of the total inductance. So inductance of the conductor 1 is due to internal flux. Okay, so it is due to the internal flux and the flux beyond d. Okay, it links a net current of 0. Okay, it does not link any current as such and does not contribute to the net magnetic flux linkages in the circuit. So what will we do is that, so I'll write down these points. This is very important point. The flux beyond d, okay, links net current of 0, net current of 0, and does not link, does not contribute, does not contribute to net magnetic field, net magnetic field. So we are here to understand the total contribution. Okay, so thus to obtain the inductance of conductor 1 due to the net external flux linkage, so what we need is that, how do we do that? So the total inductance of the conductor for these two inductance of the conductor total, if we have to calculate for, see, we have a conductor here L1, we have here L2. So L1 would have L internal plus L external. Similarly, this L2 will have L internal plus L external. So this is the total flux, total conductor. So L internal, how do we calculate? So the total inductance of a conductor would be given by inductance of conductor would be given. How it would be given? It would be given L1 would be equal to L internal plus L external, as simple as that. So L internal we saw was equal to half in 10 power minus 7 Henry per meter, and L external we just now saw 2 into 10 power minus 7 in of D by R1. This was Henry per meter. Now see, if I do some manipulation over here, manipulation, this is mathematical manipulation. What I do is that I take this thing out. 2 in 10 power minus 2 into 10 power minus 7 I take out. So I don't think I'll be able to rub this triangle at least. Okay, no problem. So I'll take this is okay. So I'll take this thing out over here. 2 into 10 power minus 7. Uh, so once I'm taking this thing out here, so I have here a half into 10 power minus 7. So instead of staying this circuit here, so I have to write 1 by 4. Okay, and here I have in d by r dash. Now if I have to write this 1 by 4 in logarithmic terms, I can write in u of 1 by 4 is nothing but equal to 1 by 4. So what I do is I substitute this equation 1. Let's be this be equation 2, equation 1 over here. I'll substitute equation 2 in 1. So what I get is that 2 into 10 power minus 7 is equal to ln of e, okay, 1 by 4 plus in d by 1, I can write plus in 1 by r dash. If I further simplify this, I can write this in terms of 2 into 10 power minus 7. Some problem is there, no problem. So I'll further simplify this in terms of 2 into 10 power minus 7. By now, most of you might have done it also. 2 into 10 power minus 7. So I'll get this in terms of in, okay, r1 e power minus 1 by 4. I can write this in r1, see, e power minus 1 by 4. If I write it down, so it is in this term only. So and little bit of mathematics in d. So this r1 e power minus 1 by 4 which you are seeing over here, this term is called r dash, which is equal to r e minus 1 by 4, which would be equal to 0.778 r. If you calculate this e power minus 1 by 4 value, it is 0.778 r, and this term is known as the self geometric mean distance. So this term is known as self geometric mean distance. So this is the term that is known as self geometric mean distance. Now of a circle, okay, of a circle with a radius r and is white and is also noted by GMR. So it is also said that this value is GMR. So this was one thing about this. Now let's suppose now we calculated this value, and let's suppose, so we have seen the value which we have got. So the value which we got was for L1. So the value for L1 we got was equal to 2 into 10 power minus 7, okay, in d by r dash, okay, because we know that r dash is nothing but r1 e minus 1 by 4, okay. So what is r dash? Basically r dash can be considered as the radius of a, see, I will write down, r dash can be considered as the radius of a fictitious, okay, fictitious conductor assumed to have no internal flux, but with a self inductance as the actual conductor with radius r, so this is what actually it means. In similar fashion, we can calculate the value of L2, okay. So L2 would be again d into 2 in 10 power minus 7 in d by r2 dash. Now this r2 dash again is nothing but 0.778 R2. That would be your e power minus 1 by 4 R2. Okay, so this is like this. So now for the complete inductance, so the complete inductance was because of L1 plus L2. So what would be the complete inductance? It would be 2 into 10 power minus 7, okay, in d by r1 dash plus 2 into 10 power minus 7 in d by r2 dash. Suppose r1 dash is equal to r2 dash, okay. So in this scenario, what would be our case? Okay, so to understand and to make you, like, I'll rub this portion over here so that it becomes very convenient. We'll write it here only, okay. And now, yes, so now let's write down. So this, if we are writing, so I can write 2 into 10 power minus 7 plus 2 into 10 power minus 7. I can write 4 into 10 power minus 7, provided your r1 dash is equal to r2 dash, and in of, okay, d of, okay, this would be equal to r1 dash r2 dash, okay. This is Henry per meter. So these are the values what we will be arriving, okay. So in other terms, if you want to give it, like, if you can write it r1 dash is equal to r2 dash, okay. This would be the, sorry, the square root here, and this equal to r dash. So then the total inductance L would be equal to 4 into 10 power minus 7 in d by r dash Henry per meter. So this is the final expression of the inductance what we are getting. So now I will just conclude my discussion. This value of inductance is called the inductance per loop meter. So whenever we are getting an inductance, so we are getting it per meter. Suppose we are getting an impedance value in case of a power transmission line, so you have to multiply it with the length of the line, okay. So per loop meter, how much is the impedance, and then the whole system whenever you are dealing with the power system scenario. This, so in the future classes we'll be understanding that in a much better way. This value of inductance what we just now saw, that is L is equal to 4 into 10 power minus 7 in d by r dash is Henry per meter. This value of inductance is called the inductance per loop meter or per loop mile. And to distinguish it from the component of the inductance of the circuit attributed to the current in one conductor only, the latter is given by one half of the total inductance of a single phase line and is called the inductance per conductor. So uh, it can be written like this. So this would be the one half of it and the other circuit would be the full of it. So this is exactly what we wanted. In the next class we will understand how to calculate for a three-phase system, the inductance calculations, then for a long transmission line, what are the types of transmission lines, pi type of network, t type of network, and velocity of a transmission line, what is the traveling waves, and further. So if you want these lectures, please stay connected to us and please subscribe it. If you are new to the channel, like, share and subscribe it. Thank you very much. I'll be concluding it. Thanks a lot for watching.